to talk about period integrals of algebraic manifolds and their differential equations.
Thank you. Today I'm going to talk about period integrals of algebraic manifolds and the differential equations that governs them. So this works together with several people, majorly with Bonglin, and then other people join in between. So I will be a little bit faster in the beginning because that part is rather classical, just motivate it. And then the rest will majorly talk about the tautological system that we introduced. So majorly we were interested in this whole thing motivated by Miller symmetry, which is one of the major developments in mathematical physics. And period integral come in a strong manner, so we pay attention to it. Then they are related to special functions and complex geometry. So at the beginning, I talked very elementary. So there are simple elementary functions, and then the hypergeometric series, which was introduced way back in 17th century. And so the important turning point is the hypergeometric equation. There's ODE defined on P1, which satisfy these equations. A, B, C fixed parameters. So every second order homogeneous linear ODE on P1 with 3 regular singular points can be transformed by linear fractional transformation to this equation. And so the hypergeometric function is a local solution to such an equation, and these are well known and can be expanded in this following form, where alpha n is defined by the gamma functions. And this guy has radius of convergence 1, and then there's any other local solution can always be obtained by analytic continuation of this hypergeometric function. So these are well known. And so I guess a major turning point was due to Legendre, where he connected to geometry of elliptic integral through the theory of elliptic integrals. So the Legendre family of elliptic curves are given by this family, where lambda is a parameter defined on C minus 0 and 1, missing out 0 and 1. And for each lambda in here, it is homomorphic to T2 is the elliptic curve, which we have a canonical identification on H upper 1, and that's isomorphic to C2. And one form is dx over y in the previous equation, and this is holomorphic on y lambda when lambda is not equal to 0 and 1, and this defines a cohomology class on here. So this vector, of course, changes holomorphically when lambda belongs to B. And it gives a canonical non-vanishing section of the flat bundle over B, whose fiber is H0 y lambda C. Given any 2 elements, the base for H lower 1 of the tori, you can write omega lambda into this form. So this is the period of the omega lambda. It's the integral of omega lambda over gamma 1 and omega lambda over gamma 2. So this is called period integral of the family. So this defines a local system on B because it admits, although it only defines locally on B, this integral admits multi-value analytic continuation along any path in B. So the period integral can be computed by, say, to the when we take A equal to B equal to half and C equal to 1, we can easily prove and check that the operator L operating on omega lambda, the differential form, satisfies this, and this is the exact form. And therefore, the integral of it is Q by this operator L. And so it satisfies this equation naturally. So therefore, the period integral satisfies the equation. So this is a simple exercise, reduce an integrating problem to a second order ODE, which further reduces to one of determining the initial conditions. So we need to solve some initial conditions. For example, at lambda equals 0, the curve y lambda developed a loop. With a little bit more work, we can show how the form omega lambda developed at pole when lambda equals 0. Then we can determine the two constants that we need to determine by the following thing. If gamma 1 is a basic one cycle on y naught that avoids a loop, then the solution must be regular in lambda, and then we know that this integral must be equal to this function. If gamma 2 is a basic one cycle that runs through the loop, then it can be shown that the solution must have a leading log singularity, and therefore omega lambda over integral omega lambda over gamma 2 is this one, log lambda plus another one, which is a unit power series determined by the equation. So this solves the problem in this one-dimensional case, computing the period integral, because we find the initial conditions, and also we solve everything here. So we try to generalize this to a more general situation. And you can write the hypergeometric equation to be integral of this form. It's just a matter of notation. So the Regenius formula gives a geometric interpretation of the integrals and allows the determination of initial condition of the equation. Similarly, we can treat the higher order integral, hyperelliptic integral, and due to Euler. So we try to generalize all these considerations to high dimension. Well, many of these considerations are related to mathematical physics in many ways, and many great mathematicians has touched this object. And modern theory starts from Gelfond School, which we shall call GKC system later. It initiates systematic study of hypergeometric functions of many variables, and they are related to modern Hodge theory developed by many, many people. Well, for us, the major motivation was coming from Miller symmetry. So we have a Collège manifold, which means the canonical bundle is trivial in this lecture. And we should have another manifold, Collège free manifold, Y tilde, which is called Miller manifold, such that so-called type 2A physics on Y is equivalent to type 2B physics on Y tilde. So this is a very important consideration. As we know, we can, once there are two physics are equivalent, we can calculate things from one theory based on other theory. And already we know that Dye, Wen, and Witten has shown the three-point function of type 2A can receive quantum corrections from wealthy instanton in every degree. And this can be thought as counting holomorphic curves in a given homology class in Y. And so these are very interesting for mathematicians because we know how to calculate holomorphic curves of certain degree. And the 2B theory can be calculated using the period integral because it doesn't have instanton corrections, as was very well known now. This is a theory about 30 years ago. Well, so let's motivate again. So omega is a holomorphic free form on the manifold, and we differentiate in the parameter space. Del A, del B, del C are the Gauss-Manin condition on the moduli space, and we differentiate it 3 times and write to omega and integrate. This gives you a number, so this is called a 3-point function. So we can, of course, write this one in terms of period integral, just similar to the elliptic curve case. We write omega to be summation omega gamma gamma. Omega gamma is the coefficient, it's just integral omega over the 3 cycles gamma. And then we can compute the 3-point function as a combination of the functions of the period integral. So that's how the 3-point functions can be computed from the period integral. And this was the major work by Candelas and his co-authors together, and also Green and Plaza. So this is a turning point of the modern mathematical physics in relate to algebraic geometry. These two works together. And they consider the family a quintic hypersurface, which is defined by this. Psi is a parameter. Psi belongs to a, say, some subset of C. And they, at the point when they consider it, they look at the orbifold construction. So they took this group, acting by scale, leaves each y psi invariant. So this orbifold reduces the Collège freeform by resolving singularity there. So these are called Miller quintic of y psi. This is a quintic, and this is a Miller of it, after taking cosine and resolve singularity. And there's a canonical holomorph freeform on the manifold. It's defined by this. And this we shall generalize also later. There always exists a canonical holomorph freeform. This period integral, the period omega over gamma, satisfy the ODE system operator. So solve this problem where theta is defined by this and C is equal to this parameter. So the singular point is where psi equal to infinity or z equals 0 is called the large complex structure limit of the family because of the unipotent action of the monogeometric group. So this is a way that we define large complex structure limit in algebraic geometry, that the monogeometric group is unipotent, maximal unipotent. So of course, it's well known that once you do this, you can compute the three-point function and obtain a very important information. And this was spectacular because this really turned mathematicians' attention to this subject after this calculation. And this can be rigorous proof for this special case. And also, it was later generalized to try to understand for curves of high genera. But this is not 100% successful, although many people are still working on it, including ourselves. Now, let's come to the major part of today's talk. So suppose we have a parameter space, which is a connected complex manifold, parameterize the Collège manifolds. And let E to be a vector bundle equipped with flat connections. This will be the Gauss-Martin connection. So we have a pairing between E and E star into OB, the usual pairing, and fix a global section on here, on E star. And this will be corresponding to the universal free form that we were interested in. The period sheaf would be just defined the following way. The image of this map, take the kernel of the Gauss-Martin connection, which simply means locally constant sections, mapping the OB by mapping gamma to gamma dot S star. Okay, so S star is an element here and paired with gamma. So that's what we call period sheaf. So now we try to be more precise now. So given a point B here, the inverse image of B would be a Collège manifold. The cohomology group of fibers form a complex vector bundle, putting into pi lower star, push down, and take the RK over B. And there's a dual bundle, E star star, has a fiber, the homology group of YBC. And there's a natural pairing between cohomology and homology. So this is a Poincare pairing. E is equipped with the Gauss-Martin connection. So now, fix an element in E star in the cohomology, represent S star B by closed form on YB. So then we can define the pairing FB to be the integral, gamma S star B to be integral there. Okay, so FB would be defined by this integral. Okay, so this we call the period integral y with respect to S star. We fix S star. Okay. So now we fix a compact Kähler manifold, D+1 dimensional. This would be, sometimes will be Fano manifold. We consider a family of hypersurface in X and consider associated flat bundle, defined this way. The subspace as a subbundle, this subspace as a subbundle, which we call X top. So this sitting E star, the point is that this top actually admits a canonical trivializing sieve, which is similar to the one that we define. In the case of Calabi-Yau, I mean the quintet, we wrote down this omega. This is the same as the one that we found. So it can be generalized to much more general situation. That's what we say here. So there exists a canonical trivializing section, which we denote by omega. So the problem that we are trying to solve is to find complete system, which we call tau, of linear PDE for this sieve. We want to compute all the sessions, local sessions of this sieve, by looking at a system of linear partial differential equation, so that the solution of this system is exactly the period integral, no more, no less. So that's the idea of trying to compute the period integral. Find a system of PDE, linear PDE, which we can calculate them explicitly. So in this way, we can calculate the integral of omega by power series, and we can also try to understand the local monogamy of the periods, and we can also compute mirror symmetry. And of course, this creates a large class of special functions on the way. So we can use this to compute instanton collections using the period integrals. And this was due to many people after the fundamental work by Canderas et al. And this monogamy problem can be used, the differential equation explicitly written down, can be used to calculate the local monogamy. And then we can also understand the degeneration of Calabi-Yau manifolds, etc. So we shall use the Riemann-Hilbert correspondency between regular holonomic D modules and pervasive sieves of Deligne and other peoples. So we will try to, this one approach we try, but we have to generalize it. And then another approach is using the reduction of post method by Duval-Griffiths. But this works better only for one parameter family of hypersurface. So let's take an example. The Legendre family of elliptic curves in P2, which we discussed earlier, can be put in the family of Lepsus pencil hypersurface of the form, where T belongs to P1. This is an example that one can use. The problem of to find a candidate of PDE system for the period sieve is that to prove completeness. So in other words, we can find a system of PDE. We can solve it, but the question is whether the solution sieve is exactly the period sieve or not. And sometimes it's not. So one has to decide, make the decision. So we developed in the last few years a approach largely based on symmetry constraint method that provides a more explicit realization of differential equations. We also studied the completeness problem associated to such an approach, which we shall discuss now. So let's, we don't have to restrict to toric manifold, but let's start here with toric manifold with first Chern class non-negative. And then we look at the universal family of Calabi-Yau hypersurface in X. So in this case, the PDE system and its solution are known explicitly. So let's take a look. So being a toric manifold, there's a toroid, which is dense inside X. And let's look at the Lie algebra of this toroid cross C star. And this, we call it T hat. Then Tx on X inducing a representation in this way is endomorphism of the anti-canonical right bundle, section of them. And this map will be defined by y to cy. So this obvious gives rise to a action here. And we have a character defined on t hat, defined by this beta TCO equals 0, beta CO1 equal to 1. So this is second. And then there's a canonical base of a canonical window given by Laurent monomial, defined the following way. Yeah. So there's a character, beta, defined t hat, which satisfies these two equations, beta TCO equals 0, beta CO1 equal to 1. And also, there's a canonical base of the sections of the entire canonical bundle given by Laurent monomials. Mu naught, mu p are t characters. So these are settings that are familiar with people who are familiar with toric manifolds. And the Peter integrals of the Calabi-Yau family are solution to the following GKC system. This one was the operator that I mentioned earlier, plus beta. Beta is a character, and acting on phi equals 0. And this operator is the operator defined in the following way, where L is the vector Cp plus 1 satisfies this equation, these two equations. So this defines a big systems of linear equations. And this system is regular holonomic. So every solution is analytic, and the solution sieve has finite rank. So that's very good. It's finite rank, and every solution is analytic. But this system is never complete. The solution sieve is always larger than the Peter sieve that we know. The Peter sieve satisfies this equation, but not identical. So we have to deal with that. Now, the ACO equal to infinity is a large complex structure, so let me tell you what ACO is. So we are going to define this section of Calabi-Yau hypersurface YF by family FA equal this. So the ACO is the ACO here, which I will come back. So the ACO equal to infinity is a large complex structure limit. This corresponding to psi that we mentioned earlier in the case of the quintic. And the degenerate Calabi-Yau manifold Y infinity is union of all T invariant toric devices in X. So this is the first point. The second point is the explicit power series formula near the infinity can be given in terms of Miller toric manifold. There is a combinatorically defined function from the neighborhood near infinity to the cohomology of the Miller manifold. So given X, there's a Miller manifold, X hat, and then the solution C of the GKC system is generated by B as an element here, paired with alpha, where alpha is in the homology of the Miller manifold. So this is what happens in the case of toric manifold. So let me be more precisely define what B is. So this was due to Hosono, Bongliang, and myself in 1995. So near the large complex structure limit, A naught equal to infinity, A naught is defined here, in B bar, the complete set of solutions to the GKC system is given by the following cohomology level function. Okay? So we define a function in this way, where T is equal to log AI and DI, which I will define a quantity a little bit later in the next session. Namely, DI are the invariant toric devices in X hat. So DI is the invariant toric devices. And then there's a Y hat. So what's Y hat? Y hat is the anti-canonical class of X hat. And then the X hat is the Miller toric manifold, combinatorically associated to X in the sense of Bertrand. And then there's M plus, which is the second homology group of X hat, the set of non-zero integral points in the Morley cone of X hat. So we are summing over M plus the Morley cone, and then Y hat is the anti-canonical divisor in X hat. And now D belongs to M plus in the Morley cone, and so we are D paired with T. T is in the second cohomology, so you can pair it. And that's OD. So what is OD? OD is defined by this. So DI are the invariant toric divisors in X hat, and you put up this little bit complicated formula. And we prove that BXT actually converges for large radius limit in the neighborhood of infinity. So this BXT defines the function in cohomology level. And when you pair with element with gamma, so pair it with alpha when you're sitting in second homology, we get the solutions to the GKC system. So this is what we claim that give a complete solution to the GKC system. So I hope this is understood. So the B series, as we defined earlier in this previous transparency, it comes from a generalization of the classical Frobenius method for solving linear ODE. So when Hosono and Bongliang and us was trying to solve the equations, we used Frobenius method to solve it. And the DIs are actually the Frobenius parameters when you try to solve ODE. So it becomes geometrically becomes the toric divisors, the formal parameters in the Frobenius method. So this has been studied later on by several people, including ourselves. Now, the example, the important example in that theorem that Hosono, Bongliang, and I did was the classical case due to Candelas. So let X to be the Miller of Pn. Then our B series reduced to this power series, which is familiar to people who has ever studied quintic Miller geometry. And the H in this case is the Frobenius parameter. It's hyperplane generator related to the equivariant cohomology. So now, expanding this powers in powers H, expanding this in powers H, the coefficient of 1 H squared H cubed are exactly 4 independent periods of the Miller quintic freeforms. But the coefficient of H power 4 is an extra solution which cannot come from a period, indicating that the GKC system is not complete in this case. And we shall see later, we can explain what this extra solution means. It corresponds to a topological 4-chain in the complement X minus Y, rather than a free cycle in the Calabi-Yau hypersurface itself. So now we try to understand the completeness problem that we mentioned earlier. So in the case X equal to Pn, the T action on the anti-canonical divisors enlarged to a bigger group, PSL n plus 1 group there. And therefore, we can get a corresponding action, SL n plus 1 plus C to the endomorphism. Previously, we just used the tori. Now we enlarge it to SL n plus 1. And with the character defined the same way, we then get an extended GKC system with a new symmetry group, which is now PSL n plus 1. So this group, after you extend it, this extend GKC system is complete. So after you enlarge the group of symmetry, the solution space becomes the period sieve of the Calabi-Yau manifold. So that's good. It solved the completeness problem in this case. So we make a conjecture which was solved in some special case. So if Y hat be the canonical class of the Miller toric manifold, then the period sieve, the Calabi-Yau manifold itself, the Calabi-Yau family itself, is precisely the sieve generated by the functions B cup product with Y hat and acting on alpha, paired with alpha, where alpha belongs to there. So this would be a very satisfactory answer to be able to calculate period sieve. And this, as I said, can be done in several cases, including an important case for PN solved by Bong Leung and his student Zhu. Oh, no, Zhu is not his student; he's a professor in Tsinghua University. Okay. Well, for toric hypersurface, the GK system gives us a candidate PDE system that is not complete. And so we would like to understand in more generally what to do. This completeness problem is actually not trivial. It's, for many cases, was not known until a few years ago. So we'd like to explain what we can do. So the basic principle is to use symmetry of X of the manifold and the geometric constraints of the family to construct a PDE system, such that the solution of the system, which we call tautological system, could include the period sieve. So period sieve would automatically solving the system, which we call tau. And we want to decide under what condition tau is complete. In other words, the solution space is exactly the period integral. So we want to do it. If we cannot prove that it's true, then we like to know the obstruction. So this is a general setting we want to put up. So we assume there's an algebraic group acting on the manifold. So a smooth projective G variety algebraic group acting on X. The notation we shall use from now on is this. L would be Kx inverse, the anti-canonical line bundle of X. V star is a section of them. And there's a map, a universal section of L, which just by taking V star cross X map to L by simply do the tautological thing. B comma X is mapped to B at X. And then we have the universal Calabi-Yau family in X, which we call pi, and Y over B. And we have the local system associated to Y. And then we look at V star cross X, which is sitting here. Subtract out F equals 0, the universal complement of the universal section. So this is notation we shall use. So let me repeat again. L is the anti-canonical line bundle. V star is X0, XL. We will study differential equation over here, over V star. And F will be defined on V star cross X as explained here. So we look at the algebra of polynomial differential operator on V star. As I said, the parameter space is on V star. So we define the Y algebra to be this, where AIs are the linear coordinates on X star. Okay, so on V star. So it's a polynomial differential operators on V star. So first of all, there's a canonical section of E star of the form where omega is a certain G invariant N form on a C star principal bundle on X. And residue is a Rayleigh-Poincaré residual map. So I indicate to you how this guy looks like in the special case of quintic already. And the residue formula shows that integral of omega over gamma is just equal to omega F over C gamma, a tube around Y gamma. Okay, so so that's just from residue formula. Now, so we have the tau system, which we call tautological system, has the following observations that we want to make. There's a universal section, actually, what we just see. So F inverse is defined on U, so then you may be not familiar with this notation yet. U is V star cross X, subtract out F equals 0. F is defined V star cross X as universal section of the line bundle. So I take F inverse over here, which is well defined. Oops. So F inverse is defined on U. And OU F inverse is a cyclic dV star module generated by F inverse. Okay? And if P belongs to dV star, which kills F inverse, then P kills the period naturally, because P kills F inverse, so it will kill everything. So this P defines a ideal. We call it an annihilating ideal of F inverse. So Jx is ideal on the dV star here. So this is good. This tells you how it kills this integral that we are interested in. And then since the group X on X for any Lie algebra element in here, theta, there's a vector field induced on V star. It also, by symmetry reason, it kills the integral. So now we have two sets of things that kills the integral. One is P, one is Z theta. So we have two sets. And we simply put them together. So Jx is the ideal, killing 1 over F, and dV star Cg is coming from symmetry. We add them together and take the cosine of dV star by this ideal. So this dV star module is called a tautological system, that we call it to be so. And this system is a good one because we proved, first of all, trivially, every period integral for the family can solve this system or equation. So this system operator all kill the period integrals. So that's good. That's what we have been looking for. Now, well, then we have to look at more detail about them. So first of all, if L is very ample, we have a canonical tautological embedding, X mapping to projective space of V. So we can identify CV to be that. And let Ix be the vanishing ideal of X sitting in the projective space. So, given the embedding of an algebraic variety in PM, you have ideal defining the variety. We define the Fourier transform of Ix to be this system. So this defines I tilde X, and we can prove that Jx that we defined earlier is generated by dV star acting on here, plus dV star acting on this Euler operator. Okay? So this is an annihilator of F inverse that we had before, the Jx. Jx was defined here, or here, the annihilating ideal of F inverse. So we have now understand how to calculate this Jx by using this embedding. If we know the embedding is explicit, we can calculate Ix explicit, and we can calculate this explicitly, of course. So we have a interesting description of Jx. Now, in general, we can replace tau, what we call tautological system, by more general system. Namely, instead of Ix, we can take any G invariant ideal. And also, we can twist the vector fields and the Euler vector fields by some Lie algebra character. This more general setup is needed to deal with families of Fano manifold and also manifold general type. Some of this calculation can be applied to manifold general type. So tau is called regular holonomic D module. Well, if it is a regular holonomic D module if X has only finite number of G orbits. So the projective group, the algebraic group, X on the projective variety, if it has only finite number of orbits, then everything is good. So in particular, any formal power series is analytic, and the C of analytic solution has finite rank at each point for this tau. And it also turns out the solution rank has a bound, is bounded by degree of the tautological embedding. if the ring is reasonably regular. So this is good. So first of all, they're finite, and also we can bound the solution space. So in the case of x equal to Pn, the Jx is generated by the following differential operators, which you can compute. And so we have a Veronese embedding, actually, in that case. And, well, this system, which we call tautological system, specialized to the previous GKG system, in case G is a tori, and is specialized to Kaplanov system, who introduced in 1997 something called wonderful compactification of a reductive algebraic group. So they're specialized to that case. And in general, if X is the projective homogeneous space by a semi-simple group, the constraint operators which defined previously actually can be computed to be this following operators, set of operators. So this was a result of, this can be derived from an old result constant, Bird constant, where CG is a quadratic Casimir operator of G acting on second order differential operators. So just give you a more concrete example, repeat example again, for the case of P2. So in the case P2, we have the group G to PSL3. L is equal to O3, and V star is symmetric product C3. And we have a Segre embedding given by this. And so therefore, the Ix that we mentioned earlier can be described by this. And the dV star is Y algebra here. So then the constraint operators that we mentioned earlier are simply this set of operators. So now, as I said, we can replace the vanishing ideal of constraint by more general ideal, G invariant ideal in the polynomial ring. And this can be used to deal with the case when Y and canonical bundle of Y is ample, very ample, and final manifold when the anti-canonical divisor is very ample. So, so let's restrict the Calabi-Yau manifold case now. Suppose X has only finite number of G obvious. Then we prove that the tautological system is regular holonomic. And the solution rank is bound above the degree of the tautological map, as mentioned earlier. This is based on the some results of Belinsky on Fourier transform and some other works by Kaplanov and Horton. So for projective toric variety, G is taken to be the dense orbit. Then we just see what we reduce to the special functions given by the cohomology value B series that we discussed earlier with Hosono. So this is the case we did in 1995 with Hosono and Bongleo. So so this, as we mentioned earlier, there's some work due to Kaplanov, which is a special case what we did here. And this is what we just mentioned earlier. And we are trying to do the Euler integral representation of these special functions, actually. We are still working on it. Now, so let's repeat again the same situation that we discussed earlier. There's a result a few years ago that we did with Spencer Brock and several others. So suppose we have projective homogeneous G space such that this mapping to here is surjective. Then the solution space at any point is canonically isomorphic to X lower n, the homology of X minus YB. The homology, the n homology of the complement of YB, of the Calabi-Yau manifold. And the isomorphism is given by the integral of a canonical defined Milomorph form, omega, cosine by F, over cycles in the complement. So this is a way that we can understand the solution space of tau. It is isomorphic to this fellow. Now, we make the assumption it's surjective, this map, but in many cases, even without this assumption, it seems to be true, the statement. So the proof is based on the method Dimker to interpret the de Rham cohomology complement in terms of Lie algebra homology of certain G modules. So when we have a projective homogeneous space, G space, then the the solution space at any point V star is canonical isomorphic to that. So so the question is, when we have this space, D module, of the repeated sieve is subset of the tau sieve, when are they complete? So when are they equal? So as a corollary of this theorem, due to these three gentlemen, tau is complete in this case, even only if the primitive cohomology equals 0. So that's good because you can check this without much difficulty. So in particular, x equal to Pn and G equal to PSLN plus 1, this system is complete. So this was conjectured in the 1990s, and now finally can be proved in this way. Now let's look at something called algebraic rank formula. Given a very ample line bundle over a projective G variety X, we look at the ring, the coordinate ring of X defined by this, and with respect to the tautological embedding, X map to PV. So let E star to be the dual representative of V given by this, mapping it endomorph of V star. And let F, we can rewrite the universal section in this way. V star cross X map to L to be AI star of that. So now we can look at the following thing. RV is the coordinate ring that I mentioned here, here. And now we tensor with EF. F is the universal section we mentioned. It has a natural dV star module structure. And the operator we just mentioned commute with dV star. And hence, we can look at this space acting by here is a submodule, dV submodule RVEF. So we can form this quotient. This quotient makes things more algebraic, and there's a canonical D module isomorphism between the tautological system with this quotient space, given by the map 1 to EF. Well, the appearance of EF actually was inspired by Borchak's work on Feynman measures. So this makes things to be more algebraic, and the right-hand side is more algebraic, so introduce some method to do calculations. And so in particular, a corollary, if X has any finite orbit G space, which we mentioned earlier, then the space of solution of the differential system at any point B is canonical isomorphic to dual of the Lie algebra co-invariant space of this type, okay? So this becomes a more Lie algebraic calculation. So for example, if G equal to PSLN and X equal to Pn minus 1, and L equal to Kx inverse, then for generic B, the monomials form a base for the Lie algebra cohomology. And this can be computed, and then we can find the dimension of it. So counting the monomials, and we found there are precisely that many solutions to the tautological system for the universal Calabi-Yau family in Pn minus 1. This allows us to prove that tau that we discussed before is complete, because the PDC for this family has this ramp. Okay, so this combined with the hyperplane section recently proved by Leung and Zhu, then we have a complete description of all PD integral of this universal family. So this answers those questions that we had a long time ago. And also, since we have this formula, we can use it to construct large complex radius limit, which was not easy before. So we just look at those elements where the rank equal to 1, because that's exactly what we need. And in this way, we can construct many space, which is a large complex structure, which we do not know before. For example, in this case, given the quintet case, and also more important is the Grassmannian case, and where we now know how to find large complex radius limit by looking at the topology of the complement of the hypersurface. So these are all quite interesting because we don't have means to find such a large complex structure limit before, especially in this case. Well, we can generalize this to more general flat variety, which I don't have time to discuss. And also, maybe I just mentioned at the very end, there was discussion about the chain integral, which I don't have time to discuss. These are the integrals that can be useful to understand some problem in Miller symmetry, which we are not completely familiar with yet. These are the extra solutions to tau that we will discuss before. And so there are applications to other things which I don't have time to talk about. These are trying to understand, construct seals of the differentiation of period integrals, and they give some interesting consequence that was not known before. So these are interesting developments, and time is up, so I stop here.
Questions?
So you mentioned a couple of times a theorem of yours was Lian,
Yeah.
and it went by a little too fast.
What?
Does that theorem show that the Hodge bundle of moduli space is trivial? Are you actually trivializing it, or does it depend on some parameters?
It depends on some parameters, yeah. Not always.
Because apparently there are physics claims now saying that that bundle is globally trivial for any Calabi-Yau, if
Right.
I understand it correctly.
Excuse me? Yeah, there's, you have mentioned about this film that we did. So this is the generalization we do for that. This is canonical holomorphic form. That's all we are trying to say. We can generalize it to more general case. This is the. Is that what you're talking? I didn't quite catch your question. This omega is a canonical holomorphic form on y tilde far side. We generalize this to more general case.
So is the section that you construct something associated just to the Calabi-Yau, or to the Calabi-Yau together with further data?
Well, we construct it associated to a principal C star bundle. I think it's with further data, yeah. Associated C star principal bundle.
Thanks.
More questions? Don't be shy.
I could ask another one. So the questions you are asking are, you give yourself a system of differential equations, and you want completeness in the sense that the only solutions come from periods.
Yeah.
But there's a stronger possible sense of completeness, namely, is the D module you're writing the D module of all equations satisfied by those, by the period functions?
Yeah, you can ask that. We have not looked into that yet. But we are pretty happy with what we achieved already.
More questions? Okay, if not, let's thank Shing-Tung again.